Next is the sampling distribution. So in this part, we will not um, compute anymore, but I will just present you how are you going to compute if you're under the sampling distribution, because this is just a parang proof that the sample is a representation of a population. So we will not compute na as in like what we did in the previous lesson po. So I will just present the computation po. So for the sampling distribution, it's just like a proof that your sample is a representation of the population, even though you will get a different numerical value from the population and the sample. Na we may get, or we will definitely get a different numerical values for each sample that you will get in the population and the population itself. But when it comes to generalization, the answer will always be the same po for the population and the given sample. So let me explain sampling distributions further with the use of an example. Suppose that a population consists of 6 employees in a small business. The random variable of interest is X and is the number of years the employee has been with the business. The values of the variable are follows. So ayun po yung table. Next, what we're going to do is, let's say we have a population as like this, and what we're going to do is we will prove that given this population, we will try to get a sample from this group, and let's see what's the difference between the numerical values with the population and the sample itself. So, for us to make the comparison between the population and the sample that we will get, so we must first get the population mean, population variance, and population standard deviation of the given data. And the formula in getting the population mean is the summation of x all over n. So what we're going to do is get the average of these numbers. In getting the average of these numbers, we'll have 1 plus 2 plus 3 plus 4 plus 5 plus 6 all over 6 since we have 6 numbers. Simplifying, we will have 3.5 as the population mean. Next is to identify the population variance and the population standard deviation. So in getting the population variance, we have the formula as the summation of the squared of the quantity of x minus the mean all over n. And then for the population standard deviation, it's just the square root of the population variance. If you can remember, we already discussed variance and standard deviation during subquarter A. But if nagtataka kayo, why is that we have a different formula for this one? It is because po, we have a different set of values wherein last subquarter, the given values are the probabilities, while in this one, the given values is just a numerical value itself, a raw numerical value. That's why there's a difference between the formulas. But anyway, we will just have the same process wherein we will construct another column for x minus mean, and then construct another column for the squared of the difference between x and the mean. And then we just get the summation of that one divided by n, then that will be the variance. Getting the summation of the last column, we will have 17.50 all over 6 since we have 6 participants. Simplifying, we will have the population variance as 2.92. Next is the population standard deviation. So all we have to do is get the square root of 2.92, and the square root of 2.92 is 1.71. So meaning the population standard deviation is 1.71. Next is we will now identify or we will now get a sample from the given population. So for step 1, we should identify how many samples do we have to get in that given population. So let's say we are asked to get 2 samples for each or for that population. So we must identify first how many possible combinations do we have if we will just get 2 samples from that population. So we will use the formula for combination na the combination of n taken n, you can try to solve it in your calculator. It is a function for combination, or if not, we have the formulas for combination as 6 factorial all over the quantity of 6 minus 2 factorial multiplied by 2 factorial. Simplifying everything, we will have 15. Meaning to say that if we will get 2 samples in that 6 population, we have 15 combinations of um, 15 combinations of samples. Since what we're going to do is to compare the samples and the population, so we must identify those 15 distinct samples with the size of 2. So doing that, we will have this table. So in this table, you can see that if we will get a sample of 2 from the given population, the possible combinations are 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 3, 2, 4, 2, 5, 2, 6, 3, 4, 3, 5, 3, 6, 4, 5, 4, 6, and 5, 6. Next is to compute the mean for this sample, and the formula that we will use to get the mean is the summation of mean or the sample mean all over the combination of n taken n, or simply the number of observations in this given table. To solve for the sample mean, we must identify first the mean for each sample, wherein you add those two numbers and you divide it by 2 na. For example, 1 plus 2 divided by 2 is 1.5. 1 plus 3 divided by 2 is 2. 1 plus 4 divided by 2 is 2.5, and so on and so forth. And then you add everything, we will have 52.5. And then we just divide 52.5 by 15, since 15 is the number of observations, and the answer is 3.5. Our sample mean is 3.5. And if you can remember, the population mean that we got is also 3.5. So there are some cases that the population mean and the sample mean is the same. But sometimes, or rarely naman, pero there are still times that the population mean and the sample mean is not equivalent. Just like what we did with the population, we must also get the sample variance and the sample standard deviation. So, the same din yung process nila, that we will add an additional column wherein we subtract the sample mean to the population mean, and then you construct another column wherein you square the difference of sample mean and the population mean. So for us to get the sample variance, all we have to do is add the numbers in the last column and divide it by the number of observations. So we add 4 plus 2.25 plus 1 plus 0.25, and so on and so forth. Then we divide it by 15. Doing so, we will have 21.5 all over 15, and the simplest form of that one is 1.43. So our sample variance is 1.43. Then for the sample standard deviation, it's just the same. We'll just get the square root of the sample variance. So getting the square root of 1.43, we will have 1.2. as the sample standard deviation. So let's now try to observe what is the difference between the population and sampling distribution, or the sample distribution that we computed a while ago. So first, the sample distribution mean is equal to the population mean. But there are still some cases wherein we get a different sampling distribution mean compared with the population mean. But the numerical values that you will obtain is closer with each other. Next is the sample mean vary from 1.5 to 5.5, whereas the population varies from 1 to 6. So as you can see, and obviously, there is a difference between the sample mean and the population. But also, if you can notice, there is no much big difference between the sample mean, the variations between the sample mean and the population mean. So this is what I'm trying to say a while ago, that there might be a difference between the numerical values that you will obtain, but the difference between those values is not quite big. Lastly, the graphical representation for the population and the sample mean change in shape from the population to the sample, as you can see in the given figure. So what we're trying to say given this figure is that as we include a lot of samples, the graph of those samples will become, or the graph might be a representation of a normal distribution most of the time, but there are still times that the graph is not a normal distribution, or it's not a graph of a normal distribution, but most cases the graph is a normal distribution. And that leads us to the next lesson, which is the central limit theorem. In this lesson, we will not compute anymore, since the computation will just be included in the next lesson na lang po. But what we're going to do is just just discuss, or just give you an overview on what central limit theorem is. So according to the central limit theorem, the sampling distribution of the mean of a random sample drawn from any population is approximately normal for a sufficient large sample size. The larger the sample size, the more closely the sampling distribution of mean will look like a normal distribution. Ngayon, why are we aiming for a normal distribution? It is because if we have a normal distribution, we can get a mean or an average, or any numerical value that is a representation of the given population. That's why you will hear some statisticians, or you will hear your research teachers, that you must include large sample sizes, because if we will get a large sample size, we can have a normal distribution. And that normal distribution, if we will have a normal distribution, the sample that you will get can most probably is also the representation of the given population. So to give you an overview of the statement of central limit theorem, we have let x be a random variable with a normal distribution whose mean is mu and the standard deviation is sigma. Let x bar be the sample mean corresponding to random samples of size n taken from the x distribution. Then the following are true. Letter A, the the sample mean distribution is a normal distribution. Letter B, the mean of the sample distribution is mu, and the standard deviation of the distribution is sigma all over the square root of n.